what I really want to talk about today is some of our experience in trying to use the SAM simulation core as a back end for part of a larger application and some of the challenges that we encountered, and express this a little bit from a somewhat naive software perspective in that I'm a mechanical engineer, I'm not an expert at software development, but trying to use SAM simulation core as part of the software like this. I think there are some things, instead of using it in a straightforward manner, you're able to make your life a little bit easier. So the whole team that worked on this was rather large. We were developing an app that I'll talk about in the next slide, but I just want to acknowledge everybody who contributed. So we have Masuda Baryaki in the top left as a graduate student, Dr. Jeffrey Brownson and Dr. Kirby Calvert, who are both at Penn State, Carolyn Fish, who's a graduate student, Dr. Frank Hardesty in the bottom left is a research faculty member. That's me in the middle, on the bottom in the green. I'm at Penn State Hazleton on the project. And we had Jangwon Su, who's a visiting faculty member, who also contributed. So the overall goal was to take a look at developing a tool that combined SAM and GIS visualization, Geographic Information System. So the idea here is that you want to be able to display the some of the solar resource and system calculations excuse me, that SAM provides on a spatial level to support decision making in an urban environment. And so a previous part of the project looked at taking LiDAR data in the city of Philadelphia and transforming that into rooftop maps, as you see in the figure here. And what we're trying to do is sort of wrap SAM's simulation core into that so that we can say, here's the rooftop. SAM, tell us what a solar system on that roof would look like in terms of output and in terms of life cycle cost and things like that. So my part of the project was looking at getting this SAM simulation core sort of wrapped up to work in that manner. So I'll give a little introduction. I'm sure a good part of this audience already knows what the SAM simulation core is, but this is the SDK that's provided by NREL for performing SAM calculations from software. They have a great set of languages that you can access it from, and they provide examples that you're able to use it. Most of the SAM model functionality is available in the simulation core, but there are a few calculations that you end up needing to do manually as compared to the desktop application. And the example that I thought of here is in the desktop application, you enter the cost component by component. What's the price per watt on the module? What's the price per watt on the inverter? Some of those calculations you have to put back together in code. So if you think about integrating this SAM simulator into a piece of software, you want the software to see SAM as simply as possible. So you want to be able to take your user inputs. In this case, we were looking to maybe allow the user to specify the electricity rate, the system lifetime, and other simple high-level parameters. Pass that into SAM, which would then act almost as a black box that the rest of the software doesn't need to understand, and then get the data out from SAM at the end. So that is able to work using the SAM simulation core examples as provided, but some of the challenges that we ran into were, one, the number of parameters. So the SAM example that runs using the PV module contained 468 parameters. So as you may guess, it's a little bit difficult to create functions that are going to accept 468 parameters. And so you need some way of sending those parameters around within the code. One of the other challenges, if you've used the SAM simulation core, is that it identifies the parameters that it's accessing using strings that would have to be hard-coded. And so in terms of fitting these calculations into a larger application, we wanted to avoid the use of those strings to limit the amount of SAM-specific details that other parts of the code needed to understand. So I just want to show you sort of the data flow of how the SAM simulation core examples work, because this was sort of demonstrates one of the other challenges that we saw. So each of these blue objects that you see is one of the modules within the SAM simulation core. So PV-SAM V1 is the photovoltaic system model tool that gives you the outputs for the electrical generation over the first year. Utility rate is a module that takes the electrical production from the array and performs the calculations that are going to tell you how much money you're going to save by having that system in that first year, and then cash loan projects that out over the lifetime of the system. So the way that this is set up, we have to set all the parameters in this data object up here at the top in red, and then we pass it through each of the modules and get that data object back out, now with outputs in there. And one of the things that we found challenging in trying to get this application to work and to test it is that as you come out of the PV-SAM V1 module, for example, the data object has changed, and then that's fed directly into utility rate with all the outputs from PV-SAM V1 already set. And so one of the things that was challenging there was just figuring out what parameters were actually brought about in the final output by PV-SAM V1, which were brought about by utility rate. It's possible to access that information through the documentation, but in terms of testing the code, we actually found that it's much easier if you revise how that data flow goes. And so what we did is we actually created objects to represent each set of parameters that go with each module. So there's a PV-SAM V1 parameters, a utility rate parameters, and so on. And then each module is called individually with those parameters. So we create a data object, pass it to PV-SAM V1, and we get that data back out. And then rather than passing that directly to utility rate, we're creating a new data object that represents the inputs to utility rate. Some of that information is going to come from data 1, and some is going to come from the utility rate parameters. We pass that through utility rate, and so on. And then we can collect all the outputs together at the bottom. So this is way more complex, and just looking at it, you should see that it's a little messier than the way the SAM examples work. But I think the real advantage that we were able to see by doing this is, like I said, it decouples the functions of each of these modules and lets you manipulate them independently. So one of the software principles that we were looking at here is trying to maintain flexibility and allow the code to work without knowing too much information about the other parts of the code. And so this was one of the tools that we used to make that happen. So when it comes to actually integrating the user inputs into the data, the way we looked at this is shown on this slide. So I mentioned we actually went ahead and created objects that represent all the parameters needed to run the module, in this case PV-SAM V1. And I mentioned before there were 460 or so parameters that were needed to run all three of those modules together. I'm not sure exactly how many corresponded to PV-SAM v1, but needless to say, it was more than we needed to actually expose to the user. So what we did in this case is allowed these to be created as a default object, and then we used an adapter shown here in black. And the adapter is sort of the code that we're using to translate the default parameters into the parameters that we want to use for this particular run of SAM. And in this case, the adapter is also using data. I'm calling it GIS data. Really, that's representing data that's coming from the GIS system. For example, the size and shape of a building that we can then use to make calculations that will be needed in order to set up these parameters. So what was interesting about doing it this way is that the bottom three blocks here are really what needs to happen if you want to run the SAM calculation. You need the parameters into the module, and then you get the output. So the adapter sort of represents the part of the code that needs to change as the intended function of the application changes. So that allows us to keep some of the parts of the code running the same way and some of the parts of the code that are going to change each time. And it does make, I'll show you, I have a slide just showing a sample pseudocode, but it sort of makes the code look a little cleaner, and you can interpret what's going on a little bit easier. So that turned out to be big. When I would find myself mired in a bug, it was a lot easier to have this nice clean code that I can really track step by step what's going on. So I just want to show here sort of to step back a level and look at the big picture of how this fit in with this ArcGIS application. So the ArcGIS plugin was able to generate these two objects that are the represent the transmission of data between ArcGIS and SAM. So one is the GIS data. I mentioned that's basically the size and shape of the buildings. One is the GUI data. So that's where we ask the user to tell us what is your electricity rate. And then those two are passed into the SSC wrapper, which operates as I showed before, and includes the adapters for each of these particular object types. We get out the orange object, which is the data from SAM, which can then be sent to the ArcGIS plugin. So then ArcGIS can ask the SAM output data, what was the system size, what were the solar savings, or anything else that you wanted to display to the user. So really what we're seeing here sandwiched in the middle is the part of the code that is SAM that we want to keep separate from the ArcGIS code. We didn't want ArcGIS to have to know that much about how SAM works for this to run. So just to show you an example of what this made the code look like, this is an example of me running PV-SAM v1. So in the first couple lines here, I'm creating a settings based on the default settings. So that has everything that you would need to run PV-SAM v1. And then what I'm going to do is manipulate that a little bit in order for me to run whatever test case I wanted. In this case, I'm taking some data from this GIS object that's passed into the function, and I'm applying settings. So I'll show you what this apply settings might look like on the next slide. But this is where the GIS data is going to be filled into those settings. Then I'm showing another example here that besides just these GIS settings, we could also have settings. In this case, I'm trying to instead of using a specific inverter on the market, because this is about rooftops of varying sizes, we were just scaling the inverter to a fixed size and using a datasheet inverter to get in the ballpark. So you could set the inverter right here using an approach like that, or you could set any other number of parameters that you would need to set to run PV-SAM v1, or alter those default values, I should say. The last step is just running that module and getting this custom output object. And again, the purpose of having the custom output object is primarily to avoid the need for the other parts of the application to use a string to access the data. So here we can have a PV-SAM v1 output that has a function such as get annual irradiance or get annual AC production. So we can use things that will be caught by the compiler rather than strings that have to be hard-coded. So this is just an example of one module. You could continue like this to run the other cash loan and utility rate modules that make up the entire run of SAM as you'd be used to seeing it in the desktop application. So this is an example of what one of those adapters looks like. So this is a run where I wanted to take this roof data in width and height and figure out what sort of array could go on there. So the first thing I'm able to set directly is just the tilt and azimuth. If you've used the SAM simulation core, you'll recognize that these field names here do match up with strings from SAM. But again, as I said, by using a field, I'm able to let the compiler to catch mistakes that I might make in the code. The other thing that I'm doing here is doing some calculations to figure out what the stringing of that array would look like, how many panels would go in series on each string, how many strings would be connected in parallel to make up the array that fits on that roof. And then I can set those values in the SAM settings, PV-SAM v1 settings as well. So, like I said, this is a work in progress, but I'm just trying to get a discussion going and share what we ran into in trying to use this. The one main point that I can share is that the SAM simulation core did work well as a backend for this larger application. It just required us to make a few modifications, or maybe not required, but we felt our lives were made easier by a few of these modifications. The main things that we ran into were just the number of inputs that SAM's looking for and how to manage that in a reduced way so that the user doesn't need to set 400 some things. And also, I've mentioned a couple times that use of string identifiers. We tried to get away from that and get into fields, again, just because of this being something that's being called from code, where if you were doing that as a script just to run calculations, the strings would really be no big deal, and it would actually maybe even be more convenient. So the last thing I want to say is that, it seems like other people who might be trying to do this type of application, we could benefit from sharing this type of experience and look at whether it makes sense to see if some sort of more universal library or universal wrapper for SAM would be convenient that would allow you to use other modules and make SAM accessible to be called as an application backend. So that's all I have to share with you today. I'd be happy to take any questions you might have or any feedback.
Great, thank you very much, Joseph. We will now open the floor to a few questions if anyone would like to ask.
Yeah, here in the room, this is Nick DiOria. And just out of curiosity, what, and you might have said this, what programming language did you use as your outside wrapper to call into SAM?
Oh yeah, I think I didn't mention that. So ArcGIS has an interface for .NET through C#. And so we were using the C# library from SAM to get this to work.
And I actually have a follow-up question to that. Is there any other language particularly that you feel would be useful to include in the SDK?
Well, there have not been languages that I've explicitly been trying to use this in, but one thing that I would say, which is another part of my research, I actually have been looking at some solar calculations on Android. I'm not sure if it's possible to get some sort of access to the SSC compiled for Android or a smartphone environment, but that's something that I would almost certainly use if it was out there. I see somebody asked on the screen here if I've ever heard of any SAM integration with Mathematica. I have not. I did see that somebody this morning was doing some integration with Excel, so I'm not familiar with Mathematica, but I was surprised to see it could work with Excel also. So it seems more flexible than is in my experience, so it's worth a try.
Here on the SAM team, we haven't explored using the SDK with Mathematica. There's a MATLAB interface provided, but we could take a look. I suspect there's some way that Mathematica can call outside libraries written in C, so if that's the case, then there should be a way to integrate SAM with it.
Joseph, if I could ask a question, I know your presentation was mostly focused on using the SAM SDK, but it looked like the application of it that you were exploring was pretty interesting. I was wondering if you wouldn't mind giving us a brief overview of what you're doing with it in the end.
Sure. So that part is not finished yet. That's still underway. There's going to be a little more information. I don't know if you're going to be at the Solar Energy Society meeting at Penn State. I know some of the guys who are working on the PV Analyst are going to be there and talking about it as well. But I can tell you a little bit. So the idea of this app was to support spatial decision-making with regard to solar energy, and we were using a case study of the city of Philadelphia where we had this LiDAR data available. And so what the intent is to allow various stakeholders to explore throughout the city what areas might be favorable for solar development, and then they could look at different geographical information related to that, such as where might we need to plan more nodes in the grid to support this additional solar development that we might expect to come up. There are tools like that out there already, and one of the advantages that we see with the tool that we're creating here is specifically that it's able to make use of SAM, which is in some cases a more sophisticated techno-economic model than what some of the other tools that already exist are using. So SAM is a little bit more reliable from that perspective, and that's what we're hoping to offer with the tool.